Well, here's a great question. Why are some nuclides radioactive? Why do they undergo different types of decay? There's alpha, beta, gamma, the different kinds. Well, we have to think a little bit more about what is a nucleus. So a nucleus is a collection of particles, right? They're called nucleons. These include protons and neutrons. And those nucleons are held together by something called the strong force. That's the actual scientific term for it, the strong force. It's a fundamental force of physics. It occurs at, acts at very short distances. I mean, because think about it. Why would all those protons be okay with being smashed together when positive charges repel, right? It's kind of hard to think about how the nucleus could be stable in the first place. The stability of that nucleus is going to be a balance between the repulsive forces between protons, right? And the attractive strong force between all of the nucleons. Okay, so we've got protons and neutrons being attracted to each other by strong force, neutrons being attracted by strong force. There is an element of strong force in attracting two protons to each other, but there's also that repulsive factor of like charges repelling. The neutrons are an important stabilizer because they are attractive to other nucleons without contributing any repulsive force. So due to the energy levels occupied by nucleons, a point is reached where the energy payback from the strong force no longer compensates for the high energy state that added neutrons must occupy. So we don't want to go there, but protons and neutrons have energy levels like electrons do. So at some point, that attraction of the strong force does not compensate anymore. So the ratio of neutrons to protons, N to Z, remember Z is the atomic number. I think it should be A, but it isn't, it's Z. N to Z, that's an important number in determining whether a nucleus is stable or not. So this is a graph. Here we have the number of neutrons on the y-axis and the number of protons on the x-axis. So this would be a line where the slope, the y over the x, or n over z, is equal to 1. And this shows us what we have here are green dots are stable nuclei. The yellow dots are unstable nuclei. So these are all the known nuclides, right? And so we see there's this line, this green area, that's called the valley of stability. So it looks a little bit like a valley in between two mountain ranges. Kind of have to use your imagination there. And we see down here for the smaller ones, these guys are going to have N to Z ratios that are close to 1. As we get higher and higher, we've got more neutrons than protons, and that ratio is above 1. The green dots end here because above 83 protons, there are no stable nuclei. They're all radioactive and falling apart. So the type of radioactivity that gets emitted depends partly on the N to Z ratio. So if your N to Z is too high, that means you've got too many neutrons. So then you're going to tend to have beta decay where neutrons get changed into protons. So you decrease the numerator and increase the denominator, and you can get your ratio closer to a stable one. If the N to Z ratio is too low, that means you've got too many protons for the number of neutrons. So those will tend to do either positron emission or electron capture, where protons get converted into neutrons. You can also have alpha decay. That will raise N to Z because you're losing you're losing protons and neutrons, and so the effect is much smaller. So looking at this valley again, if I have an isotope or a nuclide that's up here, 60 protons, in order for it to be stable, it needs a lower number of neutrons to protons. Does that make sense? It needs to go down. The ratio's too high. So there are two methods to predict the type of radioactivity. Neither of these is absolutely accurate. They're just kind of this would be a good guess kind of thing. One would be to look at that figure, the valley of stability, and to see, okay, what direction does it need to move in order to become more stable? Another way to do that is to compare the mass number of the nuclide to the atomic mass on the periodic table. So the atomic mass on the periodic table is the average of all the stable nuclei. So if we look at, say, ruthenium-112. Ruthenium, where'd you go? There you are. Element number 44. The average atomic mass of ruthenium is 101. This isotope has a mass of 112. That's a lot higher, right? It's still ruthenium. All ruthenium atoms have 44 protons. So that tells me that this guy has too many neutrons, right? That average atomic mass is going to represent an N to Z ratio that's just about right. So remember that the mass of a nuclide is going to be extremely close to its mass number, right, which is the number of protons plus neutrons. So this one has too many neutrons, and so we might predict that it would undergo beta decay to become more stable. Okay, predict whether each is likely to decay via beta decay or positron emission. So first of all, let's look back at beta decay and positron emission. So here we have beta decay, right? We're spitting out a beta particle, which is an electron. In that process, a neutron becomes a proton. So when you have beta decay, the number of neutrons decreases, the number of protons increases. So that's going to cause your N to Z ratio to get smaller, right? In positron emission, it's kind of like the opposite. We're emitting a positron instead of an electron. Now we've got a proton changing into a neutron. So our ratio is going to go up. Okay, so beta decay down, positron up. Okay, so let's look at lead 192. We're going to find it on the periodic table, and we'll see that the atomic mass of lead is 702.4. I lost it there. 207.2. I don't know what I was saying. 207.2 is the average mass of stable lead atoms. Okay. How does that compare to the mass number of this isotope? This is bigger, right? That means that this has more neutrons. How many protons does lead have? It has 82, right? So 207 minus 82 would be what, 125? And so that's going to give us a ratio 125 to 82. So that is a good ratio for lead. This one is going to be, so we got 192 minus 82, 110. So that guy would be 110 over 82. It needs to do something that's going to increase the ratio of neutrons to protons. What's that going to be? This is the one that increases it, because protons get changed into neutrons. So we would predict that that one will do positron emission. Any questions? What about lead-212? How does that compare to the average mass of stable lead atoms? 212 is bigger than 207, right? This has more neutrons than the stable ones do. So I need to go the other direction. I need my ratio to go down. So we would predict that this would undergo beta decay. How about xenon 114? So xenon, the average atomic mass is 131.3. This has an average this has a mass number that's lower. So I need to increase the number of neutrons relative to the number of protons. Yes? So how am I going to do that? Positron emission. You guys awake? You just have qual scheme things dancing in your head.
So could lead become or gold become lead?
Pardon me?
Could gold become lead if you changed its...
Yes, gold could become lead, or lead could become gold. So all those alchemists that were trying to turn things into gold, it is possible to turn things into gold. The problem is it's not economically feasible.
It's pretty cool.
Pretty cool. Yeah, pretty cool. That's for sure. But you're not going to make any money doing it. Yay, I got them right. It doesn't always happen. Magic numbers. This is where you kind of feel like scientists are kind of grasping at straws. It's like but we didn't come up with anything very good this time. We're trying to figure out, looking for patterns in all of this to see, well, what kind of patterns can we find? And there aren't really great patterns. So we got that value of stability. We have this other idea called magic numbers. So the actual number of protons and neutrons will also affect the stability, not just the ratio. So if we look at even numbers and odd numbers, so here, this is the number of stable nuclides that have an even number of protons and an even number of neutrons, 157. Right? So that's over half of them have an even number of protons and neutrons. Even number of protons, odd number of neutrons, 53. Odd and even, 50. Odd number of protons, odd number of neutrons, there's only 5. And the kind of feeble explanation for this is, well, nucleons have a tendency to pair together, much like electrons do. So we talked about spin-paired electrons in their little orbitals. Well, it turns out that the nucleons do that as well. So you've got spin-paired protons, spin-paired neutrons. And so when you have even numbers, things are happier, I guess. So you don't need to memorize that.
So the protons pair with the protons and the neutrons.
Yeah. Protons pair with protons, neutrons pair with neutrons. And again, that's all just, that's physics. Yeah. That's uncomfortable physics, right? I wanna know about the train going north at a certain speed and, that sort of thing. So, like I mentioned earlier, nucleons occupy energy levels within the nucleus, a lot like electrons do. And so just like we have elements with certain numbers, well, elements and ions with certain numbers of electrons are particularly stable, right? Like the noble gases, they're particularly stable because they have that full valence shell of 8 electrons, right? And ions that have the same number of electrons are also more stable. So atoms containing certain numbers of protons or neutrons are also uniquely stable. So if we've got N or Z equal to 2, 8, 20, 28, 50 or 82, or if we have the number of neutrons being equal to 126, those guys are stable. And notice that all of those magic numbers are even. The only thing I find remotely interesting in this is the 2 and the 8. How many valence electrons does helium have? 2. Is it stable? Very stable. How many valence electrons do the other noble gases have? 8. They're very unreactive, right? Interesting. So there it is, those magic numbers. Don't memorize them. All atoms with more than 83 protons are radioactive, and they will decay. Now, they're not just going to decay to one thing necessarily and be done. A lot of them will decay in multiple steps. So here we're looking at uranium-238. So, uranium has, 92 protons, right? So it's not going to be stable. So uranium's going to decay to thorium-234. And so that's going to be alpha decay. And we can see how this is affecting that N to Z ratio. So we're moving in this direction. And we're not going to get stable until we get to 83 or smaller. So sometimes we'll have alpha decay, sometimes beta decay. Here's a series of different alpha decay, and then we could go multiple ways here. It goes through multiple different steps where it forms a different unstable nuclide, and that one will decay. So we got mostly alpha and beta decay, and then there's gamma decay that comes along with this to get rid of the extra energy. And it will just continue until you get to a stable nuclide. And the one that uranium ends up at is lead-206. Yes?
If you have uranium, you kind of leave it alone for a while, will it naturally decay?
Yes. If you have uranium-238, eventually it will become lead-206, just all by itself. Kind of crazy, huh?
So why does, because the previous one said it was at 126 neutrons instead of the usually stable. So why does the uranium stop at 210?
That's a good question. So we said that 126 neutrons was special. So why doesn't it stop here? Well, this has 84 protons, and nothing above 83 protons is stable.
So the protons is like the leading rule for decay, that for like overall stability, those other rules can apply.
Yeah, all of those rules are just kind of observations of patterns, right? They're not really hard and fast rules. I mean, they're not even like, quantum mechanic calculations of orbitals and things. They're not that concrete. They're just, well, we've observed these characteristics. Yeah, it's all just kind of. Any other questions?